Let's look at a transformation problem in multiple integration. What we have in this problem is the computation of a definite integral over a region R where we are actually given a transformation. So like the last problem, we actually came up with one. You will have problems where the transformation will be given and you'll be expected to use it. And so we need to make sure that we understand what's going on in these types of problems. So again, the R region here is a square, but it's rotated, so it's not really the most simple region to perform a double integral. When we look at the double integral, it doesn't look difficult at all. The only problem is that the region is a little bit untoward, and we want to see if we can find something simpler. And actually, when we look at this transformation here, we can actually do that. So the transformation from S to R that's given is this one, where X is 1/2 times the quantity U plus V, and Y is negative 1/2 times the quantity U minus V. So again, we know what happens to the segments. The linear transformations are good to them. So we're going to really need to know what happens to these vertices so that we will actually have the limits of U and V in the UV plane. That is, we need to be able to describe S. So in doing that, if you look here, we'll just go ahead and multiply by 2. So 2x will be U plus V. And here multiply by -2, so -2y will be U minus V. So this is very simple to solve for U and V. In the first case, we simply add the two equations and get 2u equals 2x minus 2y, and we can eliminate the u's by subtracting, so that'll give us 2v equals 2x minus the -2y to give us the plus 2y. And then of course all the 2's absorb, and now we have u is equal to x minus y and v is equal to x plus y. So a very nice simple transformation from R into S. Now, in order to get the limits, we simply just want to see what happens to the vertices here. And so we're going to run in 0, 1, 1, 0, 1, 2, and 2, 1. And these are very simple calculations. We replace x with 0 and y with 1. So that'll give us a -1 and a 1. Likewise, for 1, 0 maps into 1, 1. 1, 2 maps into -1, 3. And 2, 1 maps into 1, 3. But that gives us our limits very simply. We see that the u's run from -1 to 1, and the v's run from 1 to 3. So we get that automatically. Now what I've done here is I've just plotted the images of the vertices here in the UV plane and just filled in the segments here. Again, we know the linear transformations take the segments into segments. So we've got a very simple region here. Again, very easy to analyze with respect to integration, a big improvement over R. Now, with the change of variables theorem, we actually need the Jacobian of this transformation, but we can get it very easily. Let's go ahead and compute the Jacobian for this transformation. Again, we have the x partials, 1 and 1, the y partials, -1 and 1 here, to give us a determinant of 2. And we know the relationship between the Jacobians, they're actually reciprocals, and so the Jacobian that we need to know is the reciprocal of this. So when we take the Jacobian of the t transformation, we just simply reciprocate 2 and get 1/2. So that's a big time saver right there. So now when we look at the original integral over R, we now write the integral over S, where we now do the compositions, that is, write x and y in terms of u and v, which were given from the original transformation, and then we have the absolute value of the Jacobian, which is the absolute value of 1/2 integrated with respect to u and v. Now the order doesn't really matter. These are fairly simple integrals, so if you did dv du, it would not matter. So we have 8, and in this case the b variable runs from 1 to 3, and the u variable runs from -1 to 1, and we simply replace x here with its definition, 1/2 times u plus v, and then we replace y with its definition, -1/2 times u minus v, and then of course we have the absolute value of 1/2 du dv. Now what you notice here is we've got 2, 2, and 2 in a negative, so we actually end up with 8 over negative 8, which is going to be a negative 1. Eventually I'm going to work that back into the integral, but I'm going to leave it outside for now. And then of course we have the u plus v times the u minus v, which is just a difference of 2 squares. So now we, again, very simple integral. We integrate with respect to u. We'll get u cubed over 3, add 1, divide by the new power, and then of course the negative uv squared, since the v is constant relative to u. And we'll do our fundamental theorem of calculus. We'll replace u in this first calculation with 1 to get a 1/3 minus v squared, and then replace u with negative 1 to get a negative 1/3 minus the negative, so that gives us a plus v squared. And now when we actually do the computation here, the 1/3s add, and of course the negative v squareds add, and we get this. So at this point, I decided to go ahead and work the negative back in. We're just going to do anti-differentiation with respect to v. So go ahead and run the negative through. That'll give you a positive 2/3 v cubed, and then the negative here, or excuse me, the negative here will just give us a negative 2/3 v. And so now we evaluate at 3 and 1. So when we replace v with 3, again, we've got a 3 cubed divided by 3, so that'll just give us a 9. 9 times 2 is 18. And then, of course, the 3 here absorbs the 3, and we get a negative 2, so 18 minus 2. Now, by the fundamental theorem for the second factor, we have minus, and then we replace v with 1. Here we get a 2/3, and replace with 1, also a 2/3. So 2/3 minus 2/3, and our answer is 16. So what we see is this problem here is just a double integral, and it's actually very simple. I just wanted to make you understand that the process of change of variables is not this. This is what we have made simple by using change of variables. That is, this integral is simple because we have an integration region that is very easy to work with. So again, change of variable is a very unique result, and you are not tied to any particular transformation. In this problem, we were actually given one, so we used it, but you can always come up with your own transformation to generate an S that makes the problem much simpler. And we are done.